April 16, 1943. Pacific Ocean Shipyard Commission, Washington, D.C. Through the large windows of the Pentagon's Naval Strategy Room, Admiral Forrester watched as rain pelted the Potomac River. Charts and production schedules covered the walls, each bearing the unmistakable signatures of American industrial might. On the central table lay reconnaissance photographs of Japanese carrier formations in the Pacific, where the Imperial Japanese Navy still maintained what many considered an insurmountable lead in naval aviation. The mathematics of carrier warfare seemed predetermined. Japan had entered the war with 10 fleet carriers, each the product of meticulous craftsmanship and years of construction. Each Japanese carrier took approximately 4 to 5 years to build, from keel-laying to commissioning. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. America, despite its industrial capacity, had entered the war with just 3 fleet carriers in the Pacific. Naval construction experts worldwide had calculated that replacing carriers lost in battle was impossible within useful timeframes. Yet within 12 months, 8 Essex-class carriers would join the American fleet. By war's end, 17 of these magnificent vessels would patrol the Pacific. What unfolded in American shipyards wasn't just a production achievement. It was the systematic demolition of the Imperial Japanese Navy's last illusion, that artisanal shipbuilding excellence could overcome what they had dismissed as American mechanical mediocrity backed by industrial mass production. The shocked Japanese naval intelligence officers would discover they hadn't been fighting ships. They had been fighting an integrated industrial system that redefined modern warfare. The American carrier program had been born from President Roosevelt's Naval Expansion Act of 1938, responding to growing tensions in both the Atlantic and Pacific. As war clouds gathered, the Navy Department under Secretary Frank Knox pressed for rapid expansion of the fleet, with particular emphasis on aircraft carriers following the lessons of early naval engagements in Europe. The Essex-class carrier design, approved in 1940, represented the culmination of American naval architecture experience. At 872 feet long, with a displacement of 27,500 tons, these vessels could carry over 90 aircraft, operated by a crew of 2,600 sailors. Their steam turbines could drive them at speeds exceeding 33 knots, fast enough to generate sufficient wind over the deck for aircraft operations even on calm days. These specifications reflected America's unique approach to naval warfare, emphasizing aircraft capacity, operational range, and damage resilience over the precision engineering that characterized Japanese vessels. Rear Admiral Kate Sullivan, director of the Bureau of Ships, represented a new generation of naval leadership. A 1922 Annapolis graduate with advanced degrees in engineering, Sullivan viewed carrier construction not as a craft, but as an industrial process where standardization, interchangeability, and production efficiency trumped customization. Her bureau had trained relentlessly in production optimization, developing techniques for modular construction and parallel assembly that would revolutionize naval shipbuilding. The yards under Sullivan's influence had practiced new welding techniques rather than traditional riveting, prefabricated major components off-site, and implemented assembly line methodologies adapted from automobile manufacturing. They turned traditional shipbuilding assumptions upside down, focusing on completion speed rather than handcrafted excellence. December 7, 1941 transformed the Essex program from important to absolutely vital. Within hours of the Pearl Harbor attack, Roosevelt summoned the nation's top industrialists to Washington. Among them was Elizabeth Kearney, president of Newport News Shipbuilding, who would become instrumental in the carrier program's success. The president's directive was simple and direct. Build me carriers. Build them faster than anyone believes possible. The following day, Congress approved the 2 Ocean Navy Act authorizing the construction of 18 fleet carriers.
Timeline proposed, completion within 24 months, seemed impossible to foreign observers. Traditional shipbuilding doctrine held that a fleet carrier required 48 to 60 months from keel-laying to commissioning. Preparing and narrating the story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The Japanese Naval Ministry, analyzing American shipbuilding capacity in January 1942, calculated that no more than 2 new fleet carriers could join the American fleet before 1944. Their assessment, based on traditional construction methods and pre-war production rates, catastrophically underestimated American industrial adaptability. They failed to recognize that American shipyards were already implementing revolutionary production techniques that would shatter every shipbuilding record. The Fore River Shipyard in Quincy, Massachusetts, normally required 180,000 man-hours to complete a destroyer. By implementing new flow production methods, they reduced this to 40,000 hours by mid-1942. This improvement factor of 4.5 applied to carrier construction suggested timeframes that seemed impossible to traditional naval architects. Construction of USS Essex, CV-9, the lead ship of the class, began at Newport News Shipbuilding on April 28, 1941. Traditional estimates projected completion in late 1944 or early 1945. The vessel was launched on July 31, 1942, just 15 months after keel-laying, and commissioned on December 31, 1942. The 20-month construction timeframe shattered all precedents in naval shipbuilding. More remarkably, this wasn't an isolated achievement. The second Essex-class carrier, USS Lexington, CV-16, was built in just 14 months at Bethlehem Steel's Fore River Shipyard. The third, USS Bunker Hill, CV-17, was completed in 17 months at the same facility. By June 1943, 5 Essex-class carriers had joined the fleet. By December, the number had risen to 8. Japanese naval intelligence initially refused to believe these reports, considering them impossible or American propaganda. What transformed American shipbuilding was the systematic application of mass production principles to what had traditionally been considered a craft industry. The Bureau of Ships under Sullivan's leadership had developed 4 key innovations that revolutionized naval construction. First was the implementation of modular construction. Rather than building carriers from the keel up in a sequential process, American shipyards divided each vessel into dozens of modules that could be built simultaneously in different locations. The massive hull was sectioned into discrete units, constructed in parallel by different teams, then brought together for final assembly. Engine rooms, crew quarters, ammunition magazines, components that traditionally required sequential construction were built as self-contained modules. These modules, some weighing hundreds of tons, were transported to the slipways by enormous cranes, where they were joined with precision that astonished traditional shipwrights. Second was the standardization of components across multiple vessels. Every Essex-class carrier used identical propulsion systems, electrical systems, pumps, valves, and thousands of other components. This standardization allowed for mass production of parts by subcontractors across the country. A pump manufacturer in Ohio could produce hundreds of identical units, achieving economies of scale impossible in traditional shipbuilding, where each vessel required custom components. Third was the revolutionary application of welding rather than riveting for hull construction. Welding required fewer man-hours, created stronger joints, reduced weight, and allowed for prefabrication of large sections away from the congested slipways. The transition wasn't without challenges. Early welded ships had suffered catastrophic failures when welds cracked in heavy seas. But by 1942, American welding technology and quality control had overcome these issues. Workers. The traditional European and Japanese shipbuilding approach utilized a single, highly skilled workforce working daylight hours. American yards implemented 3-shift operations with extensive use of female workers. The famous Rosie the Riveters, who proved equally capable of sophisticated industrial work. This tripled effective construction speed without requiring additional facilities. The human dimension of this achievement cannot be overlooked. At its peak in 1943, Newport News Shipbuilding employed over 70,000 workers, including 25,000 women who had never previously worked in industrial settings. The integration of this new workforce required innovative training programs. Sullivan's Bureau of Ships had developed accelerated training curricula that could convert office workers, homemakers, and farm laborers into skilled shipbuilders in weeks rather than the years traditionally required for apprenticeship. Elizabeth Kearney, leading Newport News Shipbuilding, implemented what she called micro-specialization, breaking complex shipbuilding tasks into smaller components that could be mastered quickly. Rather than training welders for all possible applications, she created specialized roles: hull welders, pipe welders, tank welders. This specialization allowed new workers to become productive after just 2 weeks of training, rather than the months traditionally required for apprenticeship. The logistical challenges were equally daunting. Each Essex-class carrier required 13,000 tons of steel, 8 million feet of electrical cable, thousands of valves, pumps, and specialized equipment. Traditional supply chains could never have provided these materials at the rate required. The War Production Board, established in January 1942, revolutionized industrial allocation, directing resources to shipbuilding with unprecedented authority. Steel mills that had previously produced for civilian markets were converted to naval production. Electrical manufacturers pivoted from consumer appliances to ship systems. The entire industrial base of the United States was reorganized to support shipbuilding priorities. The coordination required was unlike anything attempted in peacetime economies. The Roosevelt administration established the Production Requirements Plan that tracked every pound of steel, copper, and aluminum in the country. Behind this logistical miracle stood Captain Rebecca Martinez, Director of Material Procurement for the Navy. Her office coordinated deliveries of millions of components from thousands of suppliers, ensuring that each arrived at shipyards precisely when needed. Her innovation, the Material Staging Plan, revolutionized construction logistics by sequencing deliveries to match construction phases, preventing bottlenecks while minimizing storage requirements. The scale of material flow was staggering. At peak production, the Essex program consumed 5,000 tons of steel daily, required 500 miles of electrical cable weekly, and installed 1,500 valves per carrier. Martinez's office tracked over 100,000 different components, from tiny specialized fasteners to massive armor plates weighing dozens of tons. The precision of this supply chain management rivaled the engineering of the carriers themselves. The Japanese response to America's carrier construction miracle evolved from disbelief to dismay to strategic paralysis. In February 1943, Japanese naval intelligence received reports of 3 new Essex-class carriers operating in the Pacific. Admiral Isoroku Yamamoto dismissed these reports as American deception, convinced that no nation could build fleet carriers in less than 3 years. By April, photographic evidence confirmed the presence of 5 Essex-class carriers, with intelligence sources reporting 3 more nearing completion. Japanese naval planners faced a devastating realization. Not only could they not match American production rates, they couldn't even maintain a strategic balance. For every Japanese carrier sunk, America could build 3 replacements in the time Japan needed for 1. The psychological impact of this production disparity cannot be overstated. Japanese naval strategy had been
around the concept of decisive battle, forcing a climactic engagement that would destroy enough American naval power to force a negotiated peace. This strategy collapsed in the face of American industrial capacity. No single battle, no matter how successful, could destroy enough carriers to overcome the production differential. Vice Admiral Shigeo Shimiwa, head of Japanese naval intelligence, provided a devastating assessment in June 1943. The Americans are now commissioning more carriers every 6 months than we can build in 2 years. This production capacity represents a strategic factor that naval operations alone cannot overcome. The material quality of the Essex carriers matched their quantity. These weren't simplified or inferior vessels built to lower standards. They incorporated lessons from early war operations, featuring extensive compartmentalization for damage control, sophisticated radar systems, enlarged flight decks, improved anti-aircraft armament, and aviation facilities that could sustain higher operational tempos than their Japanese counterparts. Their design incorporated an innovation that would prove decisive in later battles: a steel flight deck
rather than the wooden deck used on earlier carriers. When Japanese kamikaze attacks began in 1944, Essex-class carriers demonstrated remarkable survivability. USS Franklin, struck by two armor-piercing bombs that penetrated to her hangar deck and ignited fueled aircraft, suffered 724 casualties, but survived damage that would have sunk any other nation's carriers. She returned to service, testament to the resilience built into every Essex. The carrier's operational capabilities exceeded Japanese expectations. Each Essex could operate over 90 aircraft, significantly more than the 72 typically carried by Japanese fleet carriers. Their larger aviation fuel capacity, more efficient aircraft handling systems, and better damage control allowed higher sortie rates. A single Essex could launch more combat sorties per day than two Japanese carriers of comparable size. The logistical support system behind these carriers multiplied their effectiveness. The service squadron system developed by Admiral William Harrington provided mobile replenishment at sea, allowing carriers to remain on station for extended periods without returning to port. Japanese carriers, limited by smaller supply vessels and less developed underway replenishment techniques, spent far more time transiting to and from bases. By August 1943, the balance of carrier power in the Pacific had shifted decisively. The Imperial Japanese Navy, which had begun the war with 10 fleet carriers to America's 3 in the Pacific, now faced 11 American fleet carriers with no capacity to close the gap. The strategic implications were devastating. Japanese naval planners had counted on a narrowing window of opportunity in 1942-43 when they held a carrier advantage. That window had not only closed, it had reversed into an insurmountable American advantage. Reichsmarshal Hermann Göring, visiting Tokyo in September 1943 to coordinate German-Japanese strategy, was reportedly stunned when shown the latest intelligence on American carrier production. Having promised Hitler that the Luftwaffe could replace combat losses at a rate British industry couldn't match, a promise that had proven catastrophically wrong, Göring recognized the strategic implications immediately. In a private meeting with Japanese Navy Minister Shigetaro Shimada, Göring reportedly exclaimed, "This is not shipbuilding, this is industrial wizardry. How can they build in months what takes us years?" The answer lay not in any single technological innovation, but in the systematic application of mass production principles to what had traditionally been considered impossible to standardize. Göring, who had failed to implement similar production reforms in German aircraft manufacturing despite repeated attempts, recognized that this production differential doomed both Axis powers to eventual defeat. The contrast between American and Japanese shipbuilding approaches could not have been starker.
Japanese carrier represented the pinnacle of craftsmanship, with components hand-fitted by skilled workers following traditions dating back centuries. Japanese naval architects emphasized quality over quantity, creating vessels of remarkable sophistication but limited in number by their artisanal production methods. Yamato-class battleships required over 2,000 workers just to manufacture the main battery turrets, each gun barrel individualized, handcrafted by master metallurgists. This approach created magnificent vessels but could never match American production rates. American shipbuilding had evolved beyond craftsmanship to process engineering. The Newport News shipbuilding documentation for Essex-class construction ran to thousands of pages, detailing every assembly sequence, material specification, and quality control procedure. This documentation allowed new workers to quickly integrate into the construction process, regardless of prior experience. What Japanese shipbuilders achieved through decades of apprenticeship, Americans accomplished through sophisticated process design and specialized training. The most remarkable aspect of the Essex carrier program was its continuous improvement. The first Essex-class carrier required 20 months to build. By 1944, construction times had dropped to 14 months, despite material shortages and manpower competition from other war industries. Each successive vessel incorporated lessons from earlier construction, refining processes and eliminating bottlenecks. Sullivan's Bureau of Ships implemented what she called the Continuous Improvement Protocol, where construction teams submitted thousands of suggestions for process enhancement. Unlike traditional military hierarchies, where innovation flowed from top to bottom, Sullivan created channels for worker-driven improvements.
The women working in the shipyards, unencumbered by traditional shipbuilding practices, proved particularly innovative in developing welding techniques and assembly sequencing that dramatically reduced construction time. The effect of America's carrier production miracle extended beyond military operations to psychological warfare. The Office of War Information made sure Japanese leaders learned about each new carrier through radio broadcasts and leaflets dropped over Japanese territories. The psychological impact of this information campaign was significant. Japanese naval officers increasingly recognized the futility of continued resistance in the face of overwhelming industrial disparity. Vice Admiral Jisaburo Ozawa, commander of Japanese carrier forces after Yamamoto's death, later admitted, "When we received confirmation of the 8th Essex carrier in December 1943, I knew the war was lost. We had no answer to American production. We could win battles, even decisive ones, but we could never overcome their industrial capacity." This recognition contributed to the strategic paralysis that characterized Japanese naval operations in late 1943 and 1944. The Essex carrier program transformed American strategic possibilities in the Pacific. When planning began for Operation Galvanic, the November 1943 assault on the Gilbert Islands, Admiral Chester Nimitz had 6 Essex-class carriers available. For Operation Flintlock, the invasion of the Marshall Islands in January 1944, he had 8. These concentrated carrier forces could generate air power exceeding anything Japan could assemble, enabling American forces to advance across the Central Pacific at a pace previously considered impossible. The Marianas Turkey Shoot in June 1944 demonstrated the culminating effect of American industrial superiority. Against 5 Japanese carriers with approximately 430 aircraft, Admiral Raymond Spruance deployed 7 Essex-class carriers as part of a force totaling 15 aircraft carriers with over 950 aircraft. The resulting battle saw Japanese naval aviation effectively destroyed as a fighting force, with over 400 aircraft lost. American carrier production had created not just a numerical advantage, but overwhelming superiority that crushed Japanese naval aviation. Captain Diana Livingston, who served as Air Operations Officer on USS Yorktown CV-10, described the operational impact in her post-war memoir. "We didn't just have more carriers, we had better carriers, operated
Crews with better training, maintained by superior logistics, supported by better intelligence." The Japanese were building individual ships. We had built an entire system of naval warfare, where carriers were just the visible component. The legacy of the Essex program extended far beyond World War II. The class formed the backbone of American naval aviation through the Korean War and into the 1960s. Several were converted to anti-submarine carriers. Others became amphibious assault ships, while some continued as attack carriers well into the Cold War. USS Lexington, the second of the class, served as a training carrier until 1991, nearly 50 years after her commissioning. More importantly, the production techniques pioneered in the Essex program transformed American shipbuilding permanently. The modular construction methods, standardization practices, and supply chain management developed for wartime production became standard practice in peacetime. The nuclear submarines and supercarriers of the Cold War era would be built using descendants of the same techniques that had shocked Göring and the Japanese in 1943. The Essex carrier program represented more than a production achievement. It demonstrated the full realization of industrial democracy's potential, the ability to channel the productive capacity of an entire society toward a unified goal. This achievement required contributions from millions of individuals, most notably the women who entered industrial work for the first time and proved that shipbuilding skill wasn't the exclusive province of men who had served lengthy apprenticeships. Sullivan's Bureau of Ships faced unprecedented challenges as 1944 dawned. While the initial 8 Essex-class carriers represented a triumph of industrial mobilization, the Pacific Campaign's expanding scope demanded even more vessels. Admiral King's strategic plan for the Pacific called for simultaneous operations in multiple theaters: the Central Pacific Thrust under Nimitz, the Southwest Pacific Campaign under MacArthur, and preparations for the eventual assault on the Japanese home islands. Each operation required carrier support, stretching even America's expanding fleet. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The logistics behind the Essex program had reached scales previously unimaginable in military history. The program now consumed 8% of all American steel production, 15% of electrical equipment manufacturing, and 6% of all aluminum output. The Bureau of Ships' massive headquarters in Washington, D.C. had expanded from 850 personnel in 1941 to over 5,000 by early 1944. An entire floor was dedicated to the Essex program alone, with walls covered in production charts tracking every aspect of construction across 7 major shipyards. Admiral Sullivan's morning production briefings had become legendary within the Navy Department. Each day began with a detailed review of the previous 24 hours' progress at every yard, identifying bottlenecks, resolving resource conflicts, and adjusting schedules to maintain momentum. Sullivan insisted on granular tracking that could identify problems before they impacted timelines. We don't measure progress in months or weeks, we measure it in shifts, in hours. Lose a day, and you might lose a battle somewhere in the Pacific. The technical evolution of the Essex class demonstrated American industrial adaptability. The first 8 Essex carriers, sometimes called short-hull Essex carriers, had been built to the original 1940 design specifications. Beginning with USS Hancock, CV-19, launched in January 1944, the design incorporated significant modifications based on combat experience. The flight deck was extended by 15 feet, the anti-aircraft batteries significantly enhanced from the original 40mm Bofors guns to the more effective 5-inch by 38 dual-purpose weapons, and the Combat Information Center enlarged to accommodate improved radar systems.
To implement such significant changes, Sullivan's team developed a system called parallel modification implementation that integrated design changes into the construction sequence without extending timelines. Changes were batched into modification packages, each implemented at specific construction milestones rather than requiring restructuring of the entire process. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The human story behind these production miracles was equally compelling. At Newport News Shipbuilding, 42% of the workforce was female by mid-1944. Women who had never seen a ship larger than a fishing boat were now constructing the most complex war machines in history. Dorothy Lancaster, who had been a department store clerk before the war, became one of the yard's most skilled welders, specializing in the intricate connections between the carrier's island superstructure and the flight deck, joints that had to withstand massive stress during flight operations. Lancaster's story, documented in a March 1944 feature in Life magazine, embodied the transformation of American society. "I'd never held a welding torch until September 1942, she told the interviewer. Now I'm responsible for welds that have to hold together when planes are landing on deck in typhoons. Sometimes I stand back and look at these enormous ships and think, I helped build that. Me, a woman who'd never built anything bigger than a dress before the war." The integration of this new workforce required both technical and cultural innovations. Elizabeth Kearney implemented what she called the partnership system at Newport News, pairing experienced male shipwrights with new female workers. Unlike traditional apprenticeships that could last years, these partnerships focused on rapid skill transfer for specific tasks. The system produced unexpected benefits. The women often developed more efficient techniques, unencumbered by traditional practices, while the men gained leadership skills many had never had the opportunity to develop. The carrier program's supply chain represented perhaps the most complex logistical undertaking in industrial history. Captain Martinez's Material Procurement Office tracked over 900,000 individual components for each Essex-class carrier, coordinating deliveries from 6,200 primary contractors and over 40,000 subcontractors. The scale of material flow was staggering. Each carrier required 13,000 tons of steel plate and structural members. 8 million feet of electrical cable, 212 miles of pipe in various diameters, 4,800 valves ranging from half-inch to massive 36-inch main seawater intakes, 32,000 light fixtures, 80 miles of ventilation ducting, and 1,400 telephones and communications devices. The precision of this supply chain became a weapon itself. Martinez pioneered what could be just-in-time delivery decades before it became standard in civilian manufacturing. Components arrived at shipyards exactly when needed, often delivered directly to installation points rather than warehouses. This system minimized storage requirements while maximizing construction efficiency. A bearing for a reduction gear would arrive the same day it was scheduled for installation, having been manufactured in Ohio, transported by rail, and delivered directly to the specific construction module where it would be used. The carrier program's growing success attracted high-level attention that threatened its momentum. In February 1944, Army General Leslie Groves, fresh from his success directing the Manhattan Project, proposed diverting steel allocation from shipbuilding to accelerate atomic bomb development. The ensuing resource battle reached President Roosevelt's desk, with Sullivan arguing forcefully that carrier construction could not be delayed without endangering Pacific operations. The debate crystallized fundamental questions about American strategy. Would the war be won through technological superiority, the promise of atomic weapons, or through overwhelming conventional force projection represented by the carrier fleet? Sullivan's presentation to the War Production Board proved decisive. Using detailed operational analyses from Pacific commanders, she demonstrated that each month of delay in carrier deliveries would cost thousands of additional casualties in amphibious operations.
Roosevelt sided with Sullivan, maintaining the Essex program's priority allocation while finding alternative resources for the Manhattan Project. The spring of 1944 marked the peak of American shipbuilding productivity. In a single extraordinary month, April 1944, American shipyards launched 3 Essex-class fleet carriers, 4 Independence-class light carriers, 7 escort carriers, 8 cruisers, 24 destroyers, 60 destroyer escorts, 35 submarines. This production feat, 141 warships in a single month, exceeded the entire pre-war Japanese naval construction program for the years 1936 to 1941 combined. The achievement represented not just industrial capacity, but organizational genius, the ability to coordinate thousands of suppliers, hundreds of thousands of workers, and millions of components into finished warships ready for combat. The implications for naval warfare were revolutionary. Traditional naval strategy centered on conserving irreplaceable capital ships, leading to caution and limited offensive operations. American production capacity created a fundamentally different strategic calculus, where carriers became expendable assets in pursuit of decisive victory. Admiral Spruance, commanding the Fifth Fleet, could plan operations with the knowledge that any losses would be replaced within months rather than years. By mid-1944, the strategic situation had been transformed. American carrier air groups could field over 1,000 combat aircraft, while Japanese naval aviation struggled to maintain 200 operational planes. This overwhelming numerical superiority was multiplied by qualitative advantages in aircraft performance, pilot training, and operational coordination. The industrial miracle of carrier construction had created the conditions for complete maritime dominance. The Japanese response to this production disparity revealed the limitations of their military-industrial system. Naval Minister Admiral Shimada ordered an emergency shipbuilding program in late 1943, attempting to accelerate completion of carriers already under construction while laying down new vessels.
The results were disastrous. Attempting to accelerate beyond traditional methodologies led to quality problems, while material shortages crippled new construction before it began. Japan's limited industrial base simply couldn't sustain simultaneous construction of multiple fleet carriers while replacing combat losses across the fleet. By diverting resources to carrier construction, other vital programs suffered. Destroyer production fell behind schedule, ammunition production declined, and aircraft manufacturing failed to meet requirements. The attempt to match American production tempo resulted not in acceleration, but in systemic breakdown. The contrast in industrial philosophy became clear in the construction of USS Ticonderoga at Newport News. When an accidental fire damaged a section of her hangar deck during construction in May 1944, traditional shipbuilding practice would have required weeks of rework, delaying completion. Sullivan's team implemented what they called parallel path resolution, continuing construction on undamaged sections while simultaneously repairing fire damage. The carrier was commissioned on schedule just 2 weeks later than originally planned, despite damage that would have caused months of delay under traditional methods. The human element of this industrial achievement extended to training carrier crews. Traditional naval practice required months of progressive training before a carrier could be considered combat-ready. The massive expansion of the fleet demanded compression of this timeline without sacrificing operational effectiveness. Captain Eleanor Wright, appointed to lead the Atlantic Fleet Carrier Training Group in March 1944, revolutionized the process through what she called modular proficiency development. Rather than sequential training where the entire ship's company progressed through stages together, Wright developed parallel training tracks where different departments could simultaneously achieve proficiency. Flight deck crews trained on shore-based mock-ups, while engineering teams operated propulsion plants at the Essex
factory before installation. When a new carrier was commissioned, these pre-trained teams merged into an integrated ships company capable of conducting flight operations within weeks rather than months. As Allied forces began planning for Operation Overlord, the invasion of Normandy, Sullivan faced a new challenge. The European theater demanded landing craft and support vessels that competed with carrier construction for resources. Rather than engaging in inter-service rivalry, Sullivan proposed an innovative solution. The Essex production system had achieved such efficiency that it now required fewer resources per carrier than originally allocated. She offered to release 15% of the program's steel allocation to landing craft production without extending carrier completion schedules. This counterintuitive proposal, accomplishing more with less, demonstrated the maturation of American production systems. Through continuous improvement, material utilization had become dramatically more efficient. Welding techniques that reduced waste, improved cutting methods that maximized yield from steel plate, and fastening systems that required fewer holes had collectively reduced material requirements while maintaining structural integrity. The summer of 1944 brought the ultimate test of American carrier production: combat losses. On June 19, 1944, during the Battle of the Philippine Sea, USS Bunker Hill CV-17 suffered severe damage from a Japanese aerial torpedo. Traditional damage assessment suggested repairs would require 6 to 8 months at a major shipyard. Sullivan's maintenance innovation, the Mobile Service Squadron, transformed this timeline. Service Squadron 10, commanded by Captain Margaret Chen, deployed a floating dry dock and repair ships to Eniwetok Atoll. Rather than sailing 6,000 miles to Pearl Harbor, Bunker Hill received repairs forward, returning to operations in just 7 weeks. This forward repair capability multiplied the effective strength of the carrier force. Rather than losing vessels for extended periods when damaged, the fleet could quickly return them to combat operations. The Japanese, lacking similar capabilities, found their effective force steadily diminishing as damaged carriers required return to home islands for repairs.
By August 1944, despite having 8 carriers nominally on their roster, Japan could field only 3 in operational condition. The industrial lessons of the Essex program spread throughout American manufacturing. The techniques developed for shipbuilding, modular construction, standardized components, process optimization, and integrated supply chains were adopted by aircraft manufacturers, tank producers, and even consumer goods industries preparing for post-war production. Sullivan became a sought-after consultant, delivering lectures at industrial conferences where manufacturing executives eagerly absorbed shipbuilding innovations. The program's success attracted international attention. In August 1944, a British industrial delegation visited Newport News Shipbuilding to study American methods. Lord Beaverbrook, Minister of Aircraft Production, reportedly remarked after touring the yard, "We are not in the same league. This isn't shipbuilding as we understand it. It's industrial production on a scale we've never imagined." After the war, Britain must either adopt these methods or cease to be a major manufacturing nation. The psychological impact on Japan's leadership reached its peak in October 1944 during the Battle of Leyte Gulf. American forces deployed 17 carriers against Japan's remaining 4 operational fleet carriers. This overwhelming numerical superiority allowed American commanders to divide their forces, simultaneously supporting the Leyte landings while intercepting multiple Japanese naval groups. The resulting battle, the largest naval engagement in history, demonstrated the strategic transformation wrought by American industrial capacity. Admiral Takeo Kurita, commanding the Central Force, later wrote in his memoirs, "When we received reports of American carrier groups both north and south of us, I realized the full magnitude of our failure. Despite our best efforts, the Americans now had such numerical superiority."
Radar operators came from diverse backgrounds that would have been unusual in pre-war military aviation. James Harrington, Bennett's radar operator, had been a radio repairman before the war with no military experience. His understanding of electronics made him invaluable despite his lack of traditional military qualifications. Throughout the night fighter force, technical expertise became as important as flying skill. The German response to these developments followed a pattern that would become familiar in technological arms races. First came denial. The losses couldn't possibly be due to new British technology. When the evidence became undeniable, they attempted to copy captured equipment, only to find they lacked the industrial base to produce critical components like the cavity magnetron. Finally, they developed countermeasures and alternative approaches, but always remained a step behind. By mid-1944, the Luftwaffe had developed window, chaff, metallized strips that created false returns on radar screens. They installed warning receivers that alerted bomber crews when they were being scanned by radar. They even experimented with radar-absorbing materials to reduce their aircraft's signatures. These measures helped, but the British simply adapted, improving their radar filtering and developing new tactics. The electronic battlefield evolved rapidly throughout 1944, with measures and countermeasures emerging in quick succession. British scientists developed circuit modifications that could distinguish between actual aircraft and chaff clouds. German engineers created more sophisticated jamming systems. Each side sought to exploit vulnerabilities in the other's electronic systems, creating a parallel competition that sometimes determined outcomes before a shot was fired. Eleanor Wright recognized the long-term implications of this trend. In a classified report in late 1944, she wrote, "We have entered an era where the electromagnetic spectrum has become as critical a battlefield as land, sea, or air. Future conflicts will be won or lost based on technological superiority in electronic systems." Her prediction would prove remarkably accurate, as electronic warfare capabilities became central to military planning in the post-war era. The radar-guided night fighters' impact extended beyond tactical success to strategic influence. By effectively neutralizing the German night bombing campaign, these aircraft freed British resources for offensive operations. The security they provided allowed Britain to commit more forces to daylight bombing of German industry rather than defining British cities.